Hello and a warm welcome to today's tutorial where we share with you information on power management solutions for industrial grids. We will start with one portion about load shedding in industrial power grids, and we will continue and close with the SICAM application generation control. My name is Michaela Mönikes. I think you might already know me from former electrification and automation webinars, and you might have met me on exhibitions where I'm a tour guide on the Siemens booth. And today I'm going to guide you through this webinar. We will have two parts, as I already mentioned, load shedding and generation control. And after each of the presentation parts, we will have a Q&A session, so questions and answers. And that's where you come into the game. It's your exclusive chance to place your question to the expert and after the presentation, receive a live answer right here from the studio. And to be honest, it's not me that will deliver the answer. I will be your voice and read your question. It's my two experts that will deliver answers. So I'm really happy that today I have with me here in the studio my dear colleague Gerhard Schubert. Well, he is an experienced technical sales consultant with a deep know-how in power management systems. And we have Anis Ben Abdel with us to complete the round because he's also an experienced technical sales consultant and he has deep knowledge in substation automation systems. And that's the perfect combination to share information on load shedding and generation control with you. And so the stage is yours.
Thank you, Michaela, for this introduction. Good morning, good afternoon, wherever you are, also from my side. As mentioned before, our names are Gerhard Schubert, and later also Anis Ben Abdel will come, and we are both working as technical sales consultants with Siemens SIEE in Germany. It's really a pleasure for us to have today here the opportunity to present in this first part of the training our SICAM load shedding solution. Frankly speaking, we will talk about all the characteristics of the features, and of course, it's interesting for you, the secrets of our solution. For easier understanding, we have structured this training into 5 sections. In the first section, we will give you 5 arguments or reasons for implementing our SICAM load shedding system. Please, Anis, could you continue?
So, thank you, Gerhard. So, before we start with the first argument, please keep in mind that when we talk about load shedding, we should always be aware that the complete breakdown of an industrial plant due to a blackout usually costs much more than the acquisition of any load shedding system. Furthermore, it should be observed that due to the phase out of fossil energy, our grids are coming close to their limits. Here as well, load shedding offers functional advantages. Let's start with the reasons. Let's start with the reason number 1. It is a typical well-known use case. Imagine that this is your industrial power grid. If a power source like the in-feeder from the public grid trips and there are no compensation measures, then the frequency will begin to decline. Depending on the characteristics of the industrial grid, this drop of the frequency will reach within short time the trigger point of all generator protection devices. This means a complete blackout for the entire production site. By using a fast power-based load shedding system, the loss of a power source is compensated within a few milliseconds by switching off low priority consumers. This prevents a blackout and keeps the impact on production as low as possible. Reason number 2, also this is a typical use case. In many industrial applications, the different processes normally do not run simultaneously. For this reason, the power generators are not designed to cover the maximum possible power consumption. However, if the power restrictions are not observed and too many consumers are switched on, then there is no longer balance between available and consumed active power. In this case, again, a frequency drop will occur. As mentioned in the previous slide, an uncompensated frequency drop will lead to a blackout with a complete loss of production. This scenario can be effectively avoided by the installation of a load shedding system. So, reason number 3 is a more sophisticated use case. Usually, the energy consumption of an industrial plant from the public grid is limited by contracts. It is a common practice to monitor the consumption in time periods of 15, 30, or 60 minutes. If a plant exceeds the contractual limit, high penalties may be accrued. A load shedding system can also monitor such contractual limits. In the shown example, the start of the energy monitoring was selected for minute 7. The load shedding system automatically extrapolates the energy consumption of 1 minute. If a violation of the contract is predicted, the load shedding system sheds the necessary number of low priority consumers. This procedure will be repeated until the end of the monitoring period. This function makes it easy to prevent possible effects of contractual violations. Other algorithms for predicting energy exceedance are also possible. So, reason number 4. Also, this is a more advanced use case. Usually, the technical limits of transformers and in-feeders are only monitored by protection relays. If the transformers or tie lines are overloaded, then they will be completely tripped by these relays. Load shedding installations can offer a much smarter approach. Just before a protection device switches off an entire transformer or a feeder, the load shedding system can shed the required number of connected low priority loads. This significantly reduces the negative impact on the plant's production. Now, we come to the last and maybe most up-to-date reason. Driven by the climate crisis and increased energy costs, many utility grid operators try to shift from classic electrical energy sources to renewable energy, such as wind or photovoltaic plants. But this also means that power reserves in the power grid will become much smaller. This fact may force operators of public grids to motivate industrial customers to help in stabilizing the grid frequency. Such a motivation can be achieved by offering lower tariff models. The installation of a load shedding system in the industrial plant enables compliance with such possible tariff models. With this message, I hand over to Gerhard for the next section. Please, Gerhard.
Okay, thank you, Arnis. Good. This section of the presentation deals now with frequency-based load shedding. Why I selected frequency-based load shedding? Because it's the simplest function. Let's start with a simple function. I will explain in detail how it works, where it can be implemented, what needs to be considered, and last but not least, how it can be applied. Good. First, let's talk in this section about the basic function of frequency-based load shedding. One of the main targets of an industrial power grid is to keep the frequency as stable as possible. As already mentioned before by Anis, if an active power source is lost, then the frequency in the power grid will start to decline. If there is no compensation, then the frequency will go down to the cut-off frequency of the generators. I'm pretty sure that you know this is the most terrible scenario for an industrial plant. Then we talk about a blackout, a complete stop of the production, really terrible. To avoid this scenario, a frequency-based load shedding system can be installed. Usually between 2 and 6 under-frequency stages are monitored. Loads with increasing priority are pre-assigned to the different stages. In case of a frequency decline, these predefined loads are tripped to restore the nominal frequency. So you see, the principle is quite simple. Good. Let's focus now on the basic architecture of a frequency-based system. The IC 61850 communication protocol offers the exchange of fast information between protection devices within milliseconds. Based on this characteristic, low frequency triggers are distributed via high priority IC 61850 goose telegrams. Among others, this solution provides following advantages. First of all, you can avoid long copper cables. You know, copper is expensive. There's no need of interposing relays because the trip is done by the load relays itself. So no interposing relays. And last but not least, you can create very flexible architectures. Frankly speaking, most of our competitors can provide almost a similar solution. But we from Siemens, our solution goes one step beyond. In our solution, the frequency assignment of the feeders can be adjusted or deactivated from the remote control center. The shown screenshot next to the monitor shows the possibility to adapt the threshold settings by the operator. Any changes from this HMI are then automatically downloaded to the protection relays of the loads. Good. Then let's come to the advantages and challenges. Frequency-based load shedding has two major advantages. For the actual frequency triggering, you neither need a controller nor any HMI. This means that you get a high availability. This also is the reason why frequency-based load shedding often is used as backup to other types of load shedding. And of course, the costs for such an implementation are quite low. But there are also challenges, which are shown here on this slide. First, the system only reacts when all the consumers also have recognized the frequency drop. This means your computers, your variable speed types, all these devices will also recognize the drop. The second challenge is considered loads which were already switched off before the frequency drop will not help in restoring the nominal frequency. This is the reason why also additional loads, spare loads, have to be tripped. But this also means that frequency-based load shedding always has to overcompensate. You switch off more loads than really required. As mentioned before, usually there are between 2 and 6 stages. But such a stage can also considered as priority level. Means that only a low number of priorities is available. Yeah, last but not least, to avoid false triggering in the event of lightning discharges. Frequency-based load shedding may not react very fast. I know one competitor solution, they focus on 3 sine waves. According to our Siemens standard, we recommend considering as a minimum 5 sine waves to be on the safe side. Good. Let's focus now on typical use cases of frequency-based load shedding in industrial grids. As shown, if you only require a simple load shedding function for the protection against the sudden loss of power, then frequency-based load shedding is a fantastic solution. Or if you only need a simple protection against overload caused by too many consumers, then it's also a suitable solution. Or the third reason, if you have already another load shedding solution and you need a backup function, take frequency-based load shedding. And finally, for supporting utility grids in stabilizing the frequency in certain cases, here also you can take frequency-based load shedding. And with this statement, I would like again to hand over to Anis.
So
Please.
Thank you, Gerhard. In section 3, I will give you an overview of our SICAM fast power-based load shedding solution. This is our main load shedding function. With this slide, I want to give you an idea of the working principle of our fast power-based load shedding solution. The system monitors the so-called contingency feeders. There are feeders that can reduce the available active power in the industrial power grid. Examples of contingency feeders are in feeders from public grids, in feeders from generators, or couplings base connecting power sources. As mentioned on this slide, the load shedding controller considers for its pre-calculation several constraints, such as the connection between consumers and active power sources, the actual consumption of the individual loads and the actual provided power of the power sources. This information can come from protection relays or power meters. Predefined priorities of the individual load, the validity of information. For example, according to our standard, a load that provides a power consumption information with invalid status is ignored, and the next load according to the priority table is considered. Last but not least, also the available power reserve of the remaining generators is observed. Taking in consideration the parameters we just mentioned, the load shedding controller pre-calculates in advance what loads need to be shed if a contingency feeder would trip. With this result of these pre-calculations, the fast power-based load shedding solution is able to compensate a loss of power source within few milliseconds. For the Siemens SICAM load shedding solution, this means, in worst case, reaction times between 30 to 70 milliseconds, depending on the involved number of IEDs and the Ethernet structure. This slide shows the basic system architecture of a SICAM fast power-based load shedding solution. As you can see, the contingency relays, the load shedding controller, and the load relays are connected to the same network. In addition, there is also an HMI from where the operator can get all required information about the load shedding function. At the HMI, the operator can also assign a priority information to each individual load. Using the received information from the contingency and the load protection relays, the singular or redundant controller is updated. With this actual information, the controller pre-calculates the so-called trip matrix. On the left side on top, you can see an example of such a table. To enable a very fast reaction, the trip matrix is stored at the IEC 61850 interface of the controller. In case of a trip of a contingency, a high priority IEC 61850 goose message is sent to the load shedding controller. The controller compares the received goose message with the stored trip matrix. And based on this comparison, in less than 10 milliseconds, all required trip goose telegrams are sent to the corresponding loads. The SICAM standard load shedding solution uses a combined system for substation automation and load shedding. To point out, the solution can be implemented in the standard substation automation hardware and infrastructure. No additional hardware is required. This characteristic provides following advantages: reduction of cost, not only in our scope of supply, for example, wiring, training, spare part, handling, etc. Providing same functionality with less hardware leads to an increased FTPF. Since we also use a combined HMI, the operator will get the same look and feel for both tasks. Even third-party protection relays can be used as contingency and load relays. But of course, if requested, independent load shedding system can be provided. Even mixed configurations using standard protection relays and load shedding output relays are possible. This slide deals with the challenges to extend a load shedding system in a working industrial plant. By extending an existing load shedding system in a working plant, following problems will appear. The devices that have to be tested are distributed all over the plant. It is not possible in a working plant to shed consumers for any test reason. But on the other hand, you need to test all load shedding functions. We solved already these challenges by providing following optional test features. At the HMI, the operator can start the test mode. This information is distributed to all load relays. In addition, the operator can replace the measured active power values at the contingency relays by simulated values. By selecting a contingency feeder at the HMI, the operator can simulate the trip of a contingency feeder. This information is sent to the corresponding contingency relays. The contingency relay treats this simulated trip like a normal trip and starts the standard load shedding process. When receiving a shed command, the load relays do not close the trip contact, but instead they return a telegram back to the HMI with the information I would have tripped. To point out, based on this optional test function, all fast power-based load shedding scenarios can be tested while the plant is still producing. Let's come now to the last slide of fast power-based load shedding, which shows possible use cases. Compared with classic frequency-based load shedding, it provides a more sophisticated function because it permanently adapts its possible reaction to the actual working mode of the grid. With other words, it does not overcompensate, and it also reacts much faster compared with frequency load shedding. Fast power-based load shedding is also very flexible. You know already this example from the first section of our presentation. As already mentioned, based on a small adaptation of fast power-based load shedding, you can observe technical or commercial limits. Gerhard, please, the stage is yours.
Okay, thank you, Anis. Good. In section 4, I would like to present some typical discussion points of fast power-based load shedding that we have noticed to our meetings with customers. To point out, here I'm really talking about real life. So one of these typical discussion points is the considered number of loads for load shedding. Especially on the Asian market, we received several times requests for thousands of individual loads to be considered for load shedding. I remember one inquiry asking for 1,600 loads, then came one with 2,000 loads, and the last one, 4,000 loads. Frankly speaking, I'm not sure if this high number of loads really makes sense, because I will explain you why. Even in a very big project, it is hard to imagine that there are thousands of completely independent processes. I would like to emphasize the word process and not load. It also makes no sense to consider all existing loads for load shedding, because for a minimum production of a plant, a higher percentage of loads must remain active. And the third argument, which I would like to give to you, is that I really doubt that the correct priorities can be assigned to thousands of individual loads. Just to give you an example from our experience, in my biggest petrochemical plant, the experienced customer had only asked to consider 120 loads for load shedding. And to point out, this requirement corresponds to our understanding. On the other hand, maybe it's just a misunderstanding. What makes sense is to provide distributed output contacts for the loads of one process. For this example, if you look at the shown picture now here, the 3 motors of a conveyor belt are installed at different locations. In such case, it would make sense to consider all IC 6150 goose message, to consider only one, this is the main message, only one IC 6150 goose message for all the 3 different output relays. It is also easy to sum up the power consumption of these 3 motors. In this scenario, the 3 motors still would count as one load for load shedding. So the message of this slide, that's the reason why I have selected this slide. Our recommendation is to count the number of individual processes and not of loads. Good. Coming to another typical discussion point. It's a very good example. It is the requirement load shedding to avoid overloading of emergency diesel generators. And frankly speaking, this request, from my understanding, is not optimal. As the name suggests, the task of an emergency diesel generator is to supply electrical energy to the critical loads during an emergency situation. In case that the emergency generators are not able to supply enough energy to all emergency loads, I would suggest you to consider a stronger EDG, or maybe to consider a spare EDG. But maybe it's again a misunderstanding. What really makes sense is to trip all loads at the start of a blackout, and then to start emergency loads step by step as soon as the EDGs, or emergency diesel generators, are able to power them. This principle prevents overloading of the EDGs during the startup procedure. But to point out, for this black start sequence, we call it black start sequence, a higher sophisticated load shedding system is not required. Yeah, another typical discussion point. Since everybody is forced to save energy, more and more industrial applications are using very efficient combined cycle generator constellations. There are many different versions of combined cycle systems, but the main principle is that the waste heat of a gas turbine is used to produce steam for a steam turbine. What now differs from project to project is the number, the size, the capacity, and the possible additional heating of the steam boiler. The challenge for fast power-based load shedding is that the possible trip of a gas turbine can also reduce the available steam for the steam turbine. But the impact, and especially the delay of the impact on the steam turbine, strongly depends on the individual characteristics of the boiler. And therefore, the customer has to provide the details of the expected reaction of the system. My recommendation, in case that no information is available, it's typically for a feed stage of a project, for example, then we suggest considering the trip of the GTG by the standard fast power-based load shedding function and the possible later impact on the STG by the dynamic power-based load shedding. So now we haven't talked about this function, but more details about this load shedding function will be given in the next section of our presentation. Let's come to another discussion point. Based on our experience, the load shedding execution time is one of the most important topics when discussing fast power-based load shedding. Let's first talk about why fast execution times are important. One reason is it means reduced mechanical stress for the remaining generators. It also means a smaller frequency impact. And the third advantage is that you get a better selectivity between fast and frequency-based load shedding. But sometimes the inquiries ask too much. For example, in one tender document, a load shedding execution time of only one millisecond was requested. First of all, when we from Siemens talk about a load shedding execution time, then we mean the time from tripping the circuit breaker at the contingency feeder to closing the trip contact at the load feeder. Coming back to the example, an execution time of 1 millisecond can only be achieved if the trip relay from the contingency feeder is also directly wired with the trip contact to the load feeder. But frankly speaking, then we are not talking about a fast power-based load shedding system. It also has to be observed that classic generators have a rotating mass. Even if we talk about small diesel generators, then it's quite common to increase the rotating mass by attaching heavy metallic wheels at the shaft of the generator. At the start of a contingency event, this remaining rotating mass will keep the frequency constant. Most industrial grids will not show any significant impact on the frequency during the very first milliseconds. In addition, it also has to be observed the circuit breaker in the tripped generator feeder will also need some milliseconds to cut the current. And based on our experience, we've never faced any problems with our load shedding execution time of 30 milliseconds for small implementations, up to 70 milliseconds for big implementations. And to point out, this given number, 30 and 70, this is really the worst case timing. Normally, our system reacts much faster. Another typical discussion point. I think several times a year, we receive inquiries where the customer is asking to extend an existing third-party load shedding system. In most cases, it is impossible to offer such an extension because of the following reasons. First of all, There is no standard for exchanging information between load shedding systems from different manufacturers. So it's not defined. If the existing load shedding system is not able to exchange information with other controllers, if it was not designed for this task, then it will be impossible to know what power will be compensated by the existing third-party system and what power shall be compensated by our new load shedding system. Also, to add time-critical information in an existing network is risky. This also has the impacts on topics like warranty, if something happens. Who is responsible for it? Cybersecurity, reaction times for old and new systems. My message to you is, if a customer really wants to combine two load shedding systems from different manufacturers, then he must clearly specify the communication interfaces and the available data of the existing systems. Just to ask for a site visit, this normally happens. They're asking for a site visit. It's not realistic. Yeah. In standard projects, fast power-based load shedding only focuses on active power. Nevertheless, sometimes we have projects where the industrial grid also consumes a significant amount of reactive power from the public grid, or where the industrial grid has problems to transmit sufficient reactive power via transformers. In such projects, we were already requested to compensate the loss of active and reactive power, and also to observe, by doing this, to observe the priorities of the loads, to point out these are too many constraints, this is not logic, it's not possible. A solution that works in most cases is to install a standard fast power-based load shedding system, and in addition, to install at critical switchgears an undervoltage protection relay for tripping loads with high reactive power consumption. I'm terribly sorry, but nevertheless, to provide a general guideline for all these scenarios is not possible. Good. Coming to the last discussion point that I want to present here. We had several times projects where the inquiry was only dealing with a load shedding system. But when it came to the project execution, the customer was asking us about the implemented generator function. Just to explain, when a generation shedding system might be required. One of these scenarios is if the industrial grid, for example, is exporting a significant amount of power. And if the connection to the public grid trips, then you understand, you have a power surplus, and then there could occur an overfrequency. And the generator protection release could cause a blackout by tripping all generators. Normally here in Europe, this happens with 50 Hertz nominal frequency, maybe you know. Normally this happens at 52 Hertz. The same might occur if a main substation in the industrial grid is lost. Also here you get the power surplus. Or another reason for this is if the granularity of the loads for load shedding is too big. But to point out, a load shedding system is not a generation shedding system. These are two different tasks. For shedding generators, completely different rules might be right. Just to give you an example, one customer had asked us to shed the generator, which is the closest to the next maintenance period. If a customer wants to get additional functions to the generation protection system, then he clearly has to mention in his tender document that he wants a generation shedding system. Otherwise, it's not part of a load shedding system. With this final statement, I'm coming to the end of this section, and again, I would like to hand over to you, Arnes. Stage is yours.
Thank you. In this last section of our presentation, I will give you an overview of our dynamic power-based load shedding solution. Dynamic power-based load shedding is a useful add-on to the already presented fast power-based load shedding function. Let's start with the basic function of the dynamic power-based load shedding. The electrical supply is one of the most important goals of the industrial power grid. For this reason, the electrical operators try to operate the local network with enough spinning reserve. Dynamic power-based load shedding helps them to achieve this goal. What does it mean? On the HMI, the operator can define a desired active power reserve. The controller permanently compares the available active power reserve in the power grid with this desired active power reserve. If the desired active power reserve is not available, then the controller starts to shed low priority loads. As you can see in this architecture, the load shedding controller receives information about the available power reserve from the primary controllers of the generators and from the public grid in feeder. On the other hand, the controller receives the current consumption of loads via the power meters or protection devices in the load feeders. Therefore, it is easy for the controller to compare the desired power reserve with the available reserve and to trip the required number of low priority loads if the desired active power reserve is not available. Now we are coming to a sophisticated function that is called gradual overload. For a certain time, classic generators can be overloaded before they become too hot and trip. To consider this possibility, our solution provides the so-called gradual overload function in the controller. Here, the user has two setting options: an integrative trigger threshold. This means that the stronger the desired power reserve is violated, the faster dynamic power-based load shedding is triggered, and vice versa. An absolute immediate trigger threshold. The advantage of this function is that short deficits in the desired spinning reserve do not cause load shedding actions. You know this example already from the first section of our presentation. As mentioned, usually transformers and transmission lines are monitored for overcurrents and temperature. The problem with classic protection is that in the event of a possible trip, the entire transformer or line is switched off. Thanks to dynamic power-based load shedding, there is a much smarter solution. Shortly before the classic protection is triggered, dynamic power-based load shedding can switch off only the overloaded, which means that there is smaller impact in the production of the plant. And finally, we come to the last slide of our presentation, which explains in detail the load inhibition function. This function does not directly refer to dynamic power-based load shedding, but it works in a similar way, and it also comes as an option. To understand this function, you have to keep in mind that motors usually require much more power during the starting process, but during this period, the cost phi is reduced to around 0.2. This also means that most of this power increase is related to reactive power. This is the reason why the load inhibit function compares the reactive power reserve of the local grid with the reactive starting power of the individual loads. if the load shedding controller detects that there is no enough reactive power reserve available, then the start of the load is prevented. There are different implementation options. With the simple solution, the load shedding controller only informs the process control center that there is now generally not enough power available to start any further motors. In the next implementation option, the controller informs the process control center in details which loads cannot be started. The third option is to provide a hardware inhibit contact at each motor feeder. And finally, the high-end version is a combination of option 2 and option 3. So, key takeaways of this training. SICAM generation control is a secondary control system, as already mentioned at the beginning, to control governors and AVR. It can be integrated within our standard substation automation system.
Yeah,
Okay.
That's interesting. I thought we talked about load shedding, right?
This is, we have the key takeaway from the other training. No?
But we have it there on the slides, right?
Yeah, we have here. Yeah. The text is it was not correct, but anyhow, we continue. As key takeaways from this training: in worst case, our provided load shedding execution time is less than 70 milliseconds. Is very important point. Even in working plants, the SICAM load shedding solution can be extended and tested, as already mentioned. SICAM load shedding can be integrated also within our standard substation automation system. So,
thank you. That was great because you already made people curious for the second part of the presentation. There we will hear something around generation control. But first we take your questions that came in for load shedding. And I start not with a question, but I've seen the chat a very friendly thank you. Yeah, come a bit closer, Gerhard. I think we will need you two experts for the questions there. In the chat, I've seen a thank you for the customer experience you shared with us. All these examples from customer, they asked for like 4,000 loads, and no, it's 120 that are the important ones. So take care of the system and place the questions there. And I think we start with the newest or with the oldest question first. That's the one really down low. So if our regie could scroll a bit down in the questions field, that will help us finding the first questions that came in. That's the dismissed ones. That's what we had in the dry run, and now we need the current ones. Oh yeah, interesting. Somebody that knows about the capabilities of us. Is it possible to use the SICAM digital twin for testing of the load shedding function?
Okay, also it's a very good question. SICAM digital twin can be used to simulate CProtect devices. Mm-hmm. For sure, CProtect devices will be used also as load devices. In this case, we have the possibility, as without hardware, without load IDs, we can simulate the load devices, and we can test the reaction matrix.
Cool.
So I think it's a very, very useful tool in this case, and it's very important to know that to test load shedding, and especially the reaction matrix. Digital twin will be very, very helpful.
So instead of playing with a real system, I just take this digital twin with all the components.
Exactly, and if I may add, for instance, I remember one project, I think it was 1 or 2 years ago in Manchester, I think 90% of the IEDs, of the protection release, were simulated using this function. So it's really useful, yes, and the answer is many times yes.
The colleagues in Indonesia also, just for information. Yeah.
So, okay, that was the CProtect, the digital twin. And now the next question that came in is, we have experts out there. So thank you, colleagues, for the questions, or thank you, interested customers, for the question. Can an 8000 device, so SICAM RTU, can this act as a load shedding output device?
Shall I?
Yes, please.
Okay.
Not me. I will listen to the answer.
Okay. The answer depends on the execution time. In our standard load shedding function, we have foreseen to consider protection release. Then we can guarantee an execution time of 30 or 70 milliseconds. If the customer grants us a little bit longer execution times, then of course also A8000 can be taken. But please consider, I would consider maybe 50 to 60 milliseconds in addition, and then also A8000 can be used as output device.
So it really depends on the configuration. We know examples where it could work, and we need to take into account what's there out in the field, right?
It depends of the reaction time.
Exactly.
It will be tolerated more than 70 milliseconds.
8000 is a little bit slower compared to CProtect 5. Yeah. That's the reason why our standard solution focuses on CProtect 5.
On a protection device to protect
protection devices. Yeah. It can be even third party. Yes.
Okay.
Yes.
Oh, perfect. And that's interesting. Is it possible to consider a redundant load shedding output devices?
Yes, also our CP8050 controller support the redundancy of IEDs. It means in this case we can have 2 output devices redundant. Also, it's possible to send simultaneous goes to both and to send the command twice. It's possible also, because we speak now about the redundancy of the load shedding controller, it's possible to take 2 controller active. It means we send always the shedding command twice, also 2 goes in this case. Yeah.
All right.
Also possible.
And now a question on spinning reserve. How is the spinning reserve considered by the fast power-based load shedding function? Whoa, that's a detailed one.
Shall I? Okay. First of all, it's a very good question. I like it because it gives me the chance to clear up a misunderstanding. Many of our customers are talking in the context of load shedding, talking about the spinning reserve. Just to point out, the spinning reserve is the reserve of the generator between the actual working point and the maximum working point. But it takes some time, it takes seconds, even sometimes a minute to reach this point. So our recommendation is we should not talk about the spinning reserve, we should talk about a fast available spinning reserve or immediate spinning reserve. And if the intention of this question was how this immediate available spinning reserve is available, yes, of course we can do that. The customer, we can have, for instance, a connection to the, and now we're coming to the generation control system, which was already mentioned.
Later.
Yeah. If we have a connection to the governor, we can get this information from the governor. We can get also an information from the customer, how fast the generator can reach a certain amount. And of course, this is considered in our load shedding system. But we have really a fantastic function. If the customer gives us the characteristic of the available generators, then we can even calculate by our own generator how much spinning reserve or fast available spinning reserve is available. So here we have really a fantastic feature.
Really interesting. Thanks. And the next one is filled with abbreviations, but I'm glad I know all of them. So DV wanted to know MGC, so the microgrid control function or the microgrid controller, also has the feature of DLS, so dynamic load shedding. How does the PMS, the power management system, standalone works differently? And can we see in the future the convergence of the power management system and the microgrid control as a packaged solution?
Shall I? Okay. Yeah. At the moment, it's not planned. If you microgrid control at the moment is not the topic, but I can tell you there is a load shedding function included that works much slower. And that's the reason if you want to have fast reaction, then you have to take the system that we have presented now. So at the moment, it's a combination of both systems is at the moment not planned.
But while I see SICAM 8 on your shirts, I think there was at least the idea to maybe migrate microgrid control also on the SICAM 8, so they will at least share the same platform, right?
The same platform. Yeah. That's correct. That's correct. Yes.
but not a packaged solution because they
the reaction time,
right?
Exactly. Yeah. Reaction time is different.
The next one is a question for me because AB wants to know, will the slides be shared after the event? And if I'm not totally wrong, they might also already be there for download. If you cannot see it, refresh it. If it's not there, you will get it via mail. And that also brings me to some more information that will be distributed via mail. You will receive access to the recording if you missed part of the presentation, and you will get some of the done homework of these two guys because the experts will, in addition to this audible answer, also deliver written answers to your questions, and we will share that information with you. We continue with a round of questions because you had some for us. Thank you for that. That was somewhere, I think, during the presentation part of Arnes in the first. Which frequency, JP wants to know, which frequency should be measured between voltage or current?
Sure.
Yeah.
Okay, let's see. Normally you have a VT on the bus bar. So normally you take from the VT, of course, you only have the voltage, so you take the frequency on the bus bar. So the standard is voltage. The answer to your question, standard is voltage. Nevertheless, we had already projects where there was no VT. And in such case, of course, you can also take, or you can elaborate the frequency from the current. But also to point out, imagine that the current through the feeder goes almost to zero. Then, of course, you don't have the frequency. But this does not matter because a feeder that has no current will not help in restoring the frequency. But you understand that the message is standard voltage. In certain cases, you can take the current.
Okay, thank you. And DW wanted to know, as the independent power producer, it always has the limit to import the active power to certain value from the power grid. I think you mentioned that a bit later in the presentation, so it might already be answered. Nevertheless, we take the question. In such a scenario, could we realize the fast load shedding to avoid importing the active power over the limit within several seconds?
Yeah, yes, of course.
It's possible, yes.
I know some projects where we have implemented that, yes. And it's really a big advantage because it avoids penalties.
Exactly.
That means money. That equals money.
A lot of money, not only for this fiscal year of the customer, but even for following fiscal years of the customers. It's a very important function, yes.
Cool. That helps paying for the system, right? Because you get savings with it.
Of course, okay. Of course. Yeah. That's the message that Arnes brought at the beginning. That's the message that Arnes brought before.
In the presentation.
One blackout costs much more than installing our integrated load shedding function. Yes.
Yeah. So, great system. And we continue the questions. So, does the load shedding controller also use the frequency and rate of change of frequency as an additional plausibility check?
You or me? Maybe,
Both can, you see experts.
maybe you have noticed several times we also have used the expression frequency stage. A stage is a combination of the frequency itself, also a certain duration of the frequency. For instance, if the frequency stays at a certain level for a certain time. And the third thing that you can also consider is the gradient, so the rate of change. That's a stage. That's normally what we consider. Of course, additional functions like plausibility check, everything can be also done. It's not really our standard, but it would be possible, of course. Yes.
Great. And next question is interesting. How does the load shedding controller look like? Well, the UI or the box?
As we use from our 8000 product portfolio, the CP8050.
I think we'll share some pictures when we find a user interface and a box. And we had a webinar on the SICAM 8000, so you can take a look at that. I think there was a screenshot in the presentation.
I would recommend to this gentleman or lady to stay with us. In the next section, you will see the 8000 controller.
Perfect. Perfect.
Stay with us.
Stay on the line. By the way, the next presentation, will it be as long as this one, or
A little bit shorter.
Perfect.
Yeah.
So we can take some more questions to load shedding. That was exactly what I hoped for. So load shedding, how many priorities does the fast load shedding system support?
Our standard is 50 priorities, but depending on the requested execution time, we can also add additional priority levels to it. So once again, the standard is 50, but it can be extended.
Okay. Next one, how much load can it handle? Well, is it a question of the size of the node?
No, I think how many?
The amount, right?
The amount, yes.
Yeah.
Let's say our maximum for the time being is 600. But I would clarify, 600 independent loads. You remember my story?
So like 600 processes, right?
No, yeah.
Yes, 600 processes. And if you ask this question about the real the loads to distribute this by context, this is unlimited. And take care of the 600 under certain conditions.
Yeah.
It means we can group loads. So,
Of course, group loads, yes.
So it's even more, and I can send out one command to like 10 loads. And
unlimited.
One for us, right?
Unlimited,
Okay.
yes.
Is the frequency-based load shedding trip load based on group under frequency stage?
Group? A group under frequency.
If a whole group goes under frequency, I think we monitor the frequency somehow, right?
Just a moment, you have a certain threshold. This can be one frequency stage, a combination of a frequency, a certain time, and a gradient.
Mm-hmm.
And by this, you can trigger or trip then an unlimited number of loads, if this is your question.
I think we try to give an answer, a written answer, and mention the question again. And if you do not think your question is answered correctly, well, contact the experts. You find their contact data in the web page, in the presentation. Feel free to ask your question directly and get on a one-on-one discussion. I'm sorry. And then next question, do you recommend to integrate the load shedding within the power control system or to have it separately?
So
Yeah, Anders, go ahead.
My personal recommendation is to save hardware. Why not to integrate it in the existing substation automation system? It's possible. For sure, we have the flexibility if you want to have, or the customer insists.
I would to add, of course, three times yes. We would recommend to have an integrated load shedding system because it saves so many things: cost, space, heat, testing, things even outside of our scope of supply. Imagine US customer, if you're a customer, I don't know, US customer, regularly you have to test the system, but if you have only one protection relay that also treats load shedding, then the test efforts are reduced. On the other side, where a separate system could add advantages is if you have an existing substation automation system, and now you want to add a load shedding system. In this certain case, you cannot test it really in a running plant. Then a separate system makes sense. Okay.
Also both
Thanks.
with
Yeah.
support, both is possible.
And saving time and money is go for the integration.
That's always good.
And our recommendation is to have an integrated system.
Yeah, fully understood. And then a question about dynamic power load shedding. Do you have a limitation about processing information from loads and probably errors caused by limitation of sending measured values from IED units? When you process like 10 values from IED with only active power, you have 1025 minus 1 combination of load shedding values that must be checked to the power deficit values?
Frankly speaking, this question is not really clear to me.
We will take that
maybe
and get it. Even when reading it, it was like so many numbers in it.
But just maybe my interpretation, please keep in mind that our controller, he always makes pre-calculation. So let's talk about fast power-based load shedding. So it makes pre-calculations. It gets, if you're talking about an integrated system, it gets the information from the IEDs and so on, pre-calculates it, and then when a trigger comes, it is very fast because everything is pre-calculated. When we're coming now to dynamic power-based load shedding, we take the same controller as a substation automation system. You do not have additional information. If the substation automation system is able to treat your information, then it's also not a problem for our dynamic power-based load shedding system.
Okay. So maybe thought a bit too complicated for this question, right?
Frankly, but I'm not about.
You will get some homework and read it again, and if you are curious, what was the question about?
Okay.
You will get the
Okay.
The next one we already had. Yes, the SICAM 8000 can be used as load shedding controller, depending on the time requirements you have on the response time,
just a moment.
right?
He's asking for a controller. And here, yes, the
Oh.
SICAM 8000 is the controller on premise. Yes, yes. The question before was related to the output, but for the controller, 3 times yes, the 8000 is the controller.
CP 8050.
Yeah.
And then the next question is interesting. Do we have any other webinars about generator shedding? Yes, it will just come and follow this one. Do we plan
Stay
an
here.
additional one? Not yet, but maybe
Not
in
yet,
future.
yeah.
But yes, we will have a generator shedding or generation control webinar in about, let me check my time, in about 6 minutes. So, one last question just rushed in. We take that and then we will have a short break and we'll be back with you. But last question, fast load shedding. Are there any limits for the number of network breakers?
I think
Probably here is related to contingency. No?
exactly contingency. Yes, 60.
Yes, there are limitations. The maximum number is 60.
Okay.
And we speak here about contingency as a critical event.
Okay.
It means, for
And
example,
for all the projects where you have experience from, that's enough, right?
Yes.
more than enough.
That's what I wanted to see. Because that, for me, that's just a number, but you know, yeah, that's 60 is.
And just to point out, to make it more precise, when we talk, he wrote network breakers, so we are talking about breakers for tie lines to public grids. What Anis mentioned, also coupling bays that are transmitting power and generator in feeders.
Yeah. Okay.
This is, in our understanding, contingency feeders or contingency breakers.
As I said, we need a 5 minute
Yes.
break, and then we'll be back with generation control. So give your eyes and ears a bit of a rest, maybe have a coffee, and then we'll be back Here it's 50 minutes after 10. I think it's 50 minutes after whatever your time is currently. So in about 5 minutes, see you again.
See you. See you.
Hello and welcome back. And as you see, we have a bit of a different light scenario right now. It seems like we do not have a nice load shedding system here, or we do have, and take the most important spots out there. So we have a bit of a problems with the light, but we know it's better than yesterday where you couldn't hear us. So, I mean, you can see us, you can hopefully hear us, and we continue with the next part of this webinar, and you will learn something about generation control. And the starting expert for that is my dear colleague, Gerhard Schubert. You already know him. He was part of the presentation around load shedding, and now you will learn on generation control. Gerhard, the stage is yours.
Thank you, Michaela. Hello again. For those of you who have not joined our previous load shedding training, my name is Gerhard Schubert, and I'm working as technical sales consultant with Siemens SIEA in Nuremberg. Together with my colleague Arnitz Belabdelcelil, you will see him later, we will give you in the following presentation some information about SICAM generation control. Okay, Arnitz, please.
So, hello everyone, good morning. If you have any questions, please feel free to use the chat function. At the end of this training, we will do our best to answer them. For better understanding, this SICAM generation control training is structured into 3 sections. In the first section, we will explain why such a control is required. Let's start with same basic definitions. To understand the overall function, we first need to talk about the so-called primary controllers. Please note the following. Classic generators are driven either by turbines or motors. The combination of drive and generator is called unit. The drive is controlled by a so-called governor, because the governor needs to know the technical details of the drive. It is usually supplied by the same manufacturer. As shown in yellow, in an island grid, the governor can regulate the rotating speed of the drive, and thus the electrical frequency in the grid. The AVR is responsible for controlling the excitation current of the generators. In an island grid, the AVR can regulate the voltage at the terminals of the generator by changing the excitation current. Both governor and AVR are called primary controllers. To point out, primary controllers are not part of our SICAM portfolio, and we do not intend to perform the primary control of turbines or generators. The SICAM generation control solution is not needed for island grids with only one generator. Where we enter the game is depicted in the next slide. Now, imagine that you have several generators in the local grid, or at least you have one generator with a connection to the public grid. In such case, the primary controllers have to be coordinated with each other and with the power exchange to or from the public grid. This requires a so-called secondary controller, and that is exactly the task of our SICAM generation control. Apart from the secondary generation control function, this slide also shows a second characteristic that must be considered. On the previous slide, it was shown that in island operation, the governor is responsible for controlling the frequency and the AVR for controlling the voltage. But as soon as the grid is coupled to a strong public grid, the frequency is defined by the large number of generators in the public grid. In this case, the governors can control the exchange of active power via the tie line to the public grid. The situation is similar with AVRs. As soon as the public grid is coupled to the local industrial network, as shown in this example, the voltage in the local network is defined by the public network. In this case, the AVRs can only control the exchange of reactive power in the link to the public grid. Let us now talk about the working modes of primary controllers. Isochronous is one of the possible working modes of the classic primary controllers. For a governor, this means that it automatically regulates the frequency at the terminals of the generator to the predefined nominal value, for example, 50 Hertz. However, it should be noted that only one governor may work in isochronous mode in an island power network. If you deviate from this restriction, then most likely the regulation starts to swing. In grid-connected mode, no local governor may operate in isochronous mode. If you deviate from this restriction, then the local generator will run either at maximum or at minimum load. The same applies to classic AVRs. Only here, the voltage at the terminals of the generator is considered instead of the frequency. If you remember, at the beginning of this training, I told you that in an island power grid with only one generator, you don't need our secondary generation control system. Now, you know that in such a small application, the primary controllers would work in isochronous mode. With this slide, we come to a second working mode that is usually provided by primary controllers, the droop mode. Let's start with the droop mode for governors. As you can see by the diagram, if a governor is working in droop mode and it has to provide more active power, then according to the droop characteristic, the governor will increase the power production at smaller frequencies. In this scenario, a possible governor working in isochronous mode would bring the frequency back to the nominal value. As you can see by the second diagram, the principle is the same for the AVR. The steeper the droop curve, the more the generator will support other generators. The advantage of the droop characteristic is that several primary controllers can work in droop mode. On this slide, I will explain the third working mode, which is almost self-explanatory. Fixed power settings are mainly used when a unit has a certain very efficient operating point, or you have a cheap drive energy that you want to use completely. As you can see, this working mode is called fixed power mode. There are 4 operating modes for how the primary controller can work together with our secondary generation control system. On this slide, we will explain the first 2 modes. The first, when one governor is working in isochronous mode, the frequency is already regulated by this primary control. In this scenario, the major advantages of our secondary control system are by shifting the droop curves of other generator up and down, the SICAM generation control enables the generator working in asynchronous mode to stay in the middle of its regulating range. By shifting the droop curves of the individual generators, also predefined load sharing can be observed. The second configuration with island operation and all governors working in droop mode is mainly used if you have a higher number of active units. In this working mode, the SICAM generation control system not only controls load sharing, but also regulates the frequency in the local power grid. Since all units will be used to reach the nominal frequency, fast regulation can be provided. In the third example, all governors working in droop mode and the plant is connected to the utility grid. In this scenario, the SICAM generation control system provides the load sharing function and regulates the power exchange with the utility grid. The fourth working mode is a special case. Sometimes in plants, you have certain power sources like waste heat. To increase the efficiency of the entire plant, such power sources can also be used to generate electrical power. However, it has to be observed that this power production is controlled by the process and not by the secondary control system. In such a case, the back pressure mode is selected for the governor, which indicates to the SICAM generation control system that the power output of the generator cannot be influenced. With this slide, I would like to hand over to Gerhard for presenting the next section. So please, Gerhard.
Thank you, Anis. Okay. Maybe you have noticed in the previous section, my colleague was dealing with general information about generation control. Now, in my section, I will explain you now in detail the characteristics of our SICAM generation control solution. Okay. Let's start with the system architecture. As you can see in this drawing, SICAM generation control can be integrated into a standard substation automation architecture. This means in detail, you do neither need any additional Ethernet cables, any Ethernet switches, or even expensive routers, so cost savings. Also, the same HMI can be used for substation automation and generation control, which provides the big advantage of the same look and feel to the operator for both applications. For smaller power grids, even the same controller, really the same controller, can be used for both tasks. And even the standard protection devices can be used to update the controller with the actual status of the power grid. Additional, as you can see, additional hardware is only needed to exchange hardware information with the primary controllers of the units. But to have a homogeneous solution, even for such we call it generator IEDs, also A8000 controllers are used. Good. One of the most important functions of generation control is load sharing. Load sharing is used to distribute the energy production or power production to the generators working in droop mode. Emphasize droop mode, according to predefined settings. And how is it done? The secondary generation control system just shifts up and down the droop curve. You've seen it before in the presentation of Anis. So it shifts up and down the droop curve of the individual generators. In order to achieve maximum flexibility, SICAM generation control considers for each individual generator two parameters. The first one is the base, we call it base point. And the second one we call participation factor. The base point specifies the operating point of a generator when the power in the grid has its nominal consumption. If the grid consumption deviates from this nominal consumption, then the second parameter, the participation factor, becomes important. It determines what percentage of the consumption deviation is provided by the generator. And now, just an example to give you an idea how the principle works. Imagine that there is a generator with a nominal active power of 100 megawatt, which is very modern and very efficient. The highest efficiency is achieved when this generator operates at 98% of its nominal power. Just imagine that. In this scenario, the customer can define 98 megawatt as the base point of and the participation factor at 0%. Means that this generator will run stably at 98% as long as more than 98 megawatt is consumed in the grid. Another example, you can see it here on the slide in the white box. Here you have a generator 1 providing 5 megawatt. And then you have the second generator providing 10 megawatt. But then suddenly somebody starts an additional process in the plant and suddenly the grid needs 20 megawatt. This means a deviation of 5 megawatt. You see, 15, 20, 5 megawatt is the difference. Since both generators have a participation factor of 50%, each of them will end at 50% of this 5 megawatt. So you see, it is quite simple. You see it in the diagram. Even if a grid is controlled by a unit working in isochronous mode, our load sharing function adapts the working points of the other generators so that the generator is working in isochronous mode, can stay in the middle of its regulating range. So you get a bigger flexibility of your grid. By considering the base points and the participation factors, all kinds of desired working modes can be realized by the SICAM generation control system. Now, let's come on this slide to another automatic function. It's the automatic topology adaptation. The present example shows the switchover from one connected power grid into two independent power grids. We call them control zones. After the switchover, one of these control zones is working in island mode, and the other one is working in grid-connected mode. SICAM generation control can treat up to 4 different control zones. Means that in case that the controller receives from the IEDs the information that a part of the power grid is separated, automatically the SICAM generation control treats this part of the power grid completely independent from other control zones. In addition, the function also automatically switches between island mode and grid-connected mode. And you might ask yourself, why is this function so important? For example, imagine that during the night shift, the connection to the public grid is interrupted. If SICAM generation control would not feature this function, then the poor operator, this poor guy, he would need not only to check the cause of the problem, but at the same time, he would also need to adapt the settings of the generation control system. Good. Another topic. Now we come to the interface between the secondary generation control system and the primary controllers. Here, we have to observe that different types of primary controllers have completely different interface characteristics. Some of them require hardwired information. Others require serial combination. Also, the way of exchanging hardwired set points can be different for each type of controller. Some of them need a certain number of pulses, others need a duration of pulses. In order to cover all these different characteristics, our interface controller offers not only high electromagnetic compatibility, but also serial, network, and hardwired interfaces. Thanks to an available functional library, different types of hardwired outputs can easily be realized. Even if an exotic function is needed, our controller has a user-definable logic function. You can see it on the slide, this logic function diagram on board. Then let's come to the HMI. The goal of this page is to give you an impression of our related HMI templates. Since the provided setpoint entry options can have a very strong impact on the entire power supply of the plant, only users with corresponding access rights can change any indicated parameter. All the details of the individual generators, the utility grid, and the available power reserve are also shown on these pictures. In particular, you can see it here, in particular, the so-called capability curve is used to provide the generator operator with information about the actual working point and the power reserves of a generator at one glance. If a SICAM generation control updates a set point for a generator, it also internally evaluates the time it will take for the generator to reach the updated value. If the new set point is not reached in time, then the control program generates an alarm message to the operator and excludes the generator from further control activity. Please kindly observe during this short session, it would take so much time to explain all the shown details. Nevertheless, if you are interested to get more information, later we can organize a separate clarification session. Yeah, here on the last slide of this section, the most important characteristics of SICAM generation control are shown. First, up to 16 units can be controlled. Then, the control program can handle up to 4 control zones, and each of them can have an individual tie line to a public grid. And here comes really something very important. And perhaps that's the most important information of this presentation. SICAM generation control is only a subset of the so-called SICAM microgrid control function. This has the big advantage that if a customer later wants to expand the industrial power grid, for example, with a PV system, with batteries, or with wind turbines, then the program is already installed and only needs to be activated. But more information about this feature I will give you in the next section. Good. In this third and final section of this presentation, I will talk about use cases of SICAM generation control. And why I say additional. I'm thinking of use cases that are not common in classic generation controls. The first is, let's call it, in the last statement, in the previous section, you remember I referred to microgrid control. So far, we have only talked about the pure generation control function. But as you can see on this page, our controller already has the built-in ability to control additional assets. This means that the SICAM generation control function can be extended by licenses also to control up to 4 additional battery controllers, 3 wind park controllers, and up to 3 PV controllers. And then the extended solution we call microgrid control. This slide refers to another possible extension of our generation control function. The microgrid controller, which includes, we have presented it before, the generation controller, can also be extended to exchange price information. It's important, price information with electrical energy aggregators. We selected this example because this additional function provides a lot of advantages to our customers. Based on this feature, the system can automatically decide, for example, to import energy from a utility grid, or to charge or discharge batteries, or to start local generators, or consider electrical energy from possible PV systems. You see, because of this possible interaction, between generation control and microgrid control, you can also enable a very economic operation. I do not know if you know the German language, but in German there's a saying, all good things come in threes. So let's end this training with a third use case. Nowadays, many of our customers are not only looking for efficient and cost-optimized power generation, but also for the reduction of CO2 emissions. And here, the extension of the generation control to the microgrid control offers additional benefits to the customer. What does it mean in detail? For example, depending on the settings of the microgrid controller, you can prefer energy from renewables, and it can decrease the power production from classic generators. And with this statement, I would like to close this training, and I would be pleased now to start our Q&A session and to answer your questions.
Thank you, Gerhard. That was an interesting glance into generation control. I think we will welcome Anis back on stage and see how many questions are already there. And as always, yeah, it will help me to see the questions there, to be able to read it to you. And you see, we still have some time, so feel free to add in your question into the system. Question to the speaker. We start with the first one I can see here. It asked there, or SG asked, can two primary controllers work in asynchronous mode?
The answer is no. Probably, Gerhard, if you... it's not recommended, and we can have a swing, no?
Yeah, the problem is, imagine if each controller would like to try to keep the frequency at, for instance, in Europe, 50 hertz. And, you know, if two systems also want to control something, then the risk is too high that you get a swing. And this should be avoided. And therefore, the standard in classic primary controlling is only to have one of them as isochronous mode controller and the others as troop mode.
Thank you. Well, and the next one is interesting. Can the same controller be used for generation control and load shedding? As we learned in the first part of the webinar, a lot of customers will start with asking for load shedding. Can they reuse the system and add generation control?
As I will say for small substation, yes, but for a big substation or large substation, we recommend controller for load shedding and another controller for generation control, as we separate
out of
controllers.
Performance reasons?
Yes.
Or, okay.
Yeah, maybe just to give you a clear picture, we had one project where we had 2 generators and 10 loads were considered for load shedding.
Mm-hmm.
In this case, yes. For if
That's
you have
small, right?
yeah, that's small. If you have bigger configurations, then please contact the Siemens headquarters for confirmation. But the standard is to have separated controllers.
So in rather few cases, you can combine it, but we do not recommend it out of performance reasons.
Exactly.
All right. Thank you. And thanks for the question. Oh, yeah, that's interesting. Do we need to add a microgrid control license if we add PV panels or photovoltaic panels to our generation control system? I think about photovoltaic plant control license there.
That depends.
Okay.
Several times a year I receive this question.
Okay.
A lot of our industrial customers, they're putting PV panels now on the roof of the plant or, for instance, on the parking lot. They ask the same question. My recommendation is, as long as the possible output of these PV panels is smaller than the biggest load in their plant, then you do not need any additional control function. You just take this as an uncontrollable generation system.
Okay.
Yeah, just you consume the power that it comes. When it is bigger, when these PV panels have more capability to supply power than the biggest load, then you should contact us.
All right, because then I need to control the
They-
generation from the panels, right?
There's a risk,
Okay.
yes, that you need
Yeah.
it. Yes.
Yeah, and that will probably, yeah, it could destroy something. I know that we had something like this in Munich on the exhibition fairground, where we had these bicycles producing energy and didn't take care of enough consumption on the booth. Yep. Think about that. So you don't, combine it again, you don't need a license. If the generation is small enough, it's smaller than the biggest load. Yeah, you mentioned that. Thank you. How does the SICAM generation control resynchronize to the public grid? Oh yeah, that's interesting in case of island mode, right?
Yes.
If the grid comes back.
I can probably try to answer the question. Also, I will say we have the option to integrate the synchronization function in our generation controller, in our controller. It means in this case it's a big advantage because the customer can save cost. Also instead of an additional device, instead of a separate synchronizing device, we have the application already or the function already integrated. What the customer needs is only a synchro check function on Z25.
I need to get the values, right? Somehow I need to get them.
Our controller is able to receive the measurement from the bus bar, from the utility transformer output, so frequency, voltage, and able also to send the regulating setting point to the generator. And so we have this function implemented.
In sync, right?
Yeah. And by the way, Siemens has a patent on this. So yeah.
A patented
Very
solution.
important.
Great.
Yeah.
Thanks. So yeah, we do not. We tell you yes, we can, but not the details, right? Oh yeah, I think we had a similar question with load shedding before, and now DV wants to know how to differentiate where microgrid control or the SICAM generation control has to be offered. So what's best for the customers? Microgrid control can also manage the generation control. Yeah, where's the difference?
Yeah, as explained before, the SICAM generation control is part of the same software as the microgrid control. So it's just a question of the licenses. If you have only pure generation control functions, no batteries, no PV panels and things like that, then our sales team will sell you the licenses for generation control.
And if I talk about a small grid, which is then a microgrid with storage, with own consumption in it, then we need a microgrid.
The additional license,
right?
as explained before, the advantage is the software will be already available in your controller.
I just need to
pay
buy for the license, right? Because I get additional functionality. Thanks for the question. And we take the next one. Is the fixed generation mode of a generator the same as the base load mode of a generator?
No.
Base load fixed generation mode.
No. As explained before, sometimes you have generators that are very efficient. And then you take this, for instance, this. What you can do, maybe to explain another way. Some governors have this fixed mode, but you can achieve the same functionality, and the question is good. You can achieve the same functionality by programming this fixed the base point with a participation function or a percentage of 0. Then both functions are the same. Yeah, thank you for this question.
Great one. And MS wants to know, what would be the solution if there were more than 16 generators at the plant?
Then please contact us.
We have a solution for that, but that's not the
maximum
standard
number is 16.
right?
Okay. The limit.
Yeah, but please contact us. There are always tricks and things. Maybe we find a solution.
You have some ideas for that.
Of course,
I
we are flexible.
Yeah, we have some solutions there. And then KK wants to know if we can sell a touch panel for the HMI for smaller installations. I'm pretty sure we can, right?
Of course. This has at the moment not really to do with generation control or load shedding, but we have several solutions for that, for instance. And now we are talking about our E8000 system. Maybe you know we have an integrated web HMI function so that you can connect any panel that offers a HTML browser function. But
so I can put a tablet on there. And
for instance, of course, yes.
HTML5.
Yeah.
HTML5,
well, that's common with most browsers, isn't it?
Yeah. It's a very cheap, it's a very economic solution.
Yeah, that's true. Yeah, I've seen that before. And then next question, how do we know the minimum megawatt power when the generator stays in ISOC mode? How much is the minimum load of each generator? And how do we know about this?
That's a very good question, but if I would be you, I would ask the provider of the generator, because if it is Siemens Energy, it really depends on the characteristic of the individual generator. And by the way, for designing or for configuring our system, we need such information.
So the information is available, and it's
should,
needed as
it should be available by the
input for the
exactly.
control,
Yeah.
but we cannot deliver it, right? Because it's a question of the hardware, of each individual hardware. All right, thank you. And then next question, is the generator control function part of the integrated solution to load shedding function and active power control? Well, if I got it right,
my understanding is correct, there are two different and dependent applications.
Okay,
yeah. Load shedding and generation control.
Okay.
But maybe may I come back to the question before? Sure. Okay, I'm sorry. Maybe I understood it in a wrong way. Just to explain the principle, normally you have one generator which works. If it is a smaller constellation, you have one generator working in isochronous mode. And then you have other generators helping this generator, supporting it, working in troop mode. Okay, in this constellation, the generator, if you don't have a secondary control, the first generator working in isochronous mode must have the capability to compensate the smallest load of the grid or the highest amount of the grid. Yeah, if you don't have a secondary generation control. By the help of our system, we can also influence the generators working in troop mode so that the first generator always remains in the middle of the isochronous mode. Okay, so it's coming back to this question, let's say we have a very good solution for that, but for the individual application, please come back to us. We have to know all the characteristics of all of the available generators. But I'm pretty sure we have a very good solution for that. Okay.
Thank you. So back to the minimum load on the generator, right? And yeah, we've seen that we have two different applications for load shedding and for generation control.
Exactly.
Thank you so much for your valuable questions. They were really happy with your questions, so thanks for that. I was really happy with the answers. I hope you learned a lot. I did, once again. That's why I like this electrification and automation webinars. We will continue them. I think if you are already registered for them, you will receive the invitations for following ones. I know next week we'll talk about how to get insights in low voltage grids, and probably even more on the agenda. For today, I'd say keep your systems protected, keep your motors up and running, or get them in perfect load shedding mode, and see you next time. Goodbye.
Thank you.
See you. Bye. Thank you.